So, we know where and when our packets appear in our solution. The next big question, though, is how big are these packets? In other words, since these give us probability densities, what is the probability contained in each of these packets? The total probability in the reflected packet, of course, represents the total probability that any given particle would be reflected, and likewise for the transmitted packet. So let's begin to think about calculating, for instance, the reflection probability. So mathematically what we would do is we would basically take a region, like I've sketched for you here, and integrate up the total probability that appears under this region, so that we are capturing only the reflected probability. If we think a little bit more about this, the safest time to do that would be at a very large positive time out in the future. Because at a large positive time, this packet will be completely isolated by itself. And if I reach that type of a point, well, really, I could just take the total area under the reflected packet. So that gives us our first clue, really, of how to calculate this probability. We just want the total probability contained in psi of r. So let's take a look at how that would appear. So if I want the probability of reflection, what I'm saying is I could get it by integrating over all possible positions the probability that comes just from the contributions associated with that reflected packet, because that's what will give me the area under that backward moving peak that contains the probability for my reflected particles. Now, I've got psi of r written up there for you. I'd like to rewrite just this piece by itself so we can really contemplate calculating this integral. So if I take my integral, right, which has all of these other factors in it that you might recall, there's the normalization, it has its peak so that we're sure we're taking wave functions or an incoming state that has momenta that are mostly very near k naught. We have the 1 over root 2 pi, so we have properly normalized momentum states. And now my job is just to take the reflected piece. And that had this interesting prefactor, you will recall, k1 minus k2 over the sum of k1 plus k2. You have to be a little careful because remember always that k2 is actually technically a function of k1. So that also is a variable during my integration over k1. Then we have, of course, the backward moving momentum state associated with my packet. And finally, we have those time-dependent pieces, which have their standard form like so. Now, let's think about what this is going to involve, right? And this is, of course, for any time t. Once we get this, of course, later on, we can evaluate it for some very large time in the future. Now, as we look at this, you'll notice, oh dear, right? What this is, it's some complicated function of k1. So I'm going to be doing some kind of Fourier transform. That's because I've got this e to the I k1x. And when I'm Fourier transforming, oh wow, it looks like one of these Gaussian functions. It has this other piece that depends on k squared. So I'm going to be doing some kind of crazy completing the square. I might be able to do that, right? And then, though, I have to deal with this function that's multiplying that Gaussian. That makes it even worse. This could start to get pretty bad. And then my reward for doing this nasty Fourier transform is going to be then to square that nastiness and then do another integral of it. So that doesn't seem necessarily like the best option. That's something we could do, but we might want to look for another approach. One of the beauties of quantum mechanics is in quantum mechanics you always have options. There's almost always 2 or 3 different ways to calculate exactly the same thing. So we might want to think about another way to find the total probability associated with my packet. And as we contemplate that, one thing that I'd like you to consider, or for you to notice, is that right now I'm considering adding up the probabilities as a function of position in my position representation. But what I have here for my position representation looks a whole lot like a Fourier transform. Right? This is really just a superposition of pure states of momentum. These here are my pure states of momentum, right? This 1 over 2 pi multiplies this. This is some pure state of momentum. It happens to have a momentum minus k1 of x, but it's a pure state of momentum nonetheless. So this looks like a quantum superposition. And in fact, I know the weights in my quantum superposition. So I could actually, instead of doing this in the position representation, let's use our other option we always have in quantum mechanics. We also have a momentum representation. I could get exactly the same probability from Parseval's theorem by integrating not psi of r, but the momentum representation for psi of r. Of course, modulo squared, so that I'm getting probabilities. And these momentum amplitudes are exactly what multiplies these momentum states. And I know what those are. Here, I'll just circle what all those pieces are. It's a little crazy, but I think I can do this, right, like so. All of this, then, is what gives me the weights on those different momentum eigenstates. So I really can just take these and integrate their square. So let's continue along that vein. That at least saves me one of two very nasty integrals that I would have to do. So this is dk. Then if I copy all my factors properly, 2 sigma squared on pi to the 1/4 power e to the minus sigma squared, k1 minus k0, it's a Gaussian quantity squared. Then I have my interesting factor k1 minus k2, which remember is technically a function of k1, over the sum, right? I don't have the 2 pi because that's part of my momentum state. I don't have this factor. That's part of my momentum state. But I do have this time-dependent factor, e to the minus I h bar k1 squared over 2m times t. And this whole business is modulo squared. Okay, that saved me one big integral. Now I can think about simplifications. Well, there's one big simplification jumping out at me because remember, I only need the magnitude of this thing. And this quantity, a phase factor, always has amplitude 1 or complex magnitude 1. And that's not going to affect the overall magnitude. So I could just scratch this off right away. Another quick way to see that is, remember, the magnitude of a product is always the product of the magnitudes. So I could write it as this magnitude times this magnitude. Of course, don't forget I had the magnitude squared, so I have to square both of the pieces that I factor out. But then, of course, this just has modulo unity. That term goes away. So that was nice. Good, we're making progress. Now here's the one tricky thing that we're going to do here. I want you to notice something. This particular factor here has a very special job, right? That is what we put in, if you remember, at the very beginning of the day, right, to make this incoming wave packet piece be our standard normalized free space wave packet. That is the whole purpose of these weights. It makes a nice normalized packet, but the particular packet it makes has momenta distribution P of k, and it's P of k1 because I'm writing everything as a function of k1, is peaked when k1 is near k0. So I have this very sharp peak there, like so. Now, those factors, right, are going to be very sharply peaked, concentrated at one particular value of k0. And what that represents physically, the physical idea behind all of that, is that I'm sending here, my whole premise is I'm sending in a particle of energy E, which would mean I have a well-defined energy for my incoming particle, which gives it a well-defined momentum, and I'm trying to determine how much reflection and transmission I get depending upon this energy or well-defined momentum. But of course, quantum mechanics doesn't ever allow us to have a completely precisely well-defined momentum. That's why I'm making a superposition of a series of momenta, but my whole job in setting up an appropriate experiment is to keep the momenta tightly concentrated around k0. So I'm really trying to sample what's happening in the close vicinity of this k0. This other piece of my function, what I'd like you to notice about it is that this is not a particularly peaked function, right? It's just some k minus k over k plus k. This piece is going to be a very smooth type of a function if I've done my experimental design quite properly to make my experimental design very tightly focused. And you guys have been with me through this kind of thing before. This looks like how we do an integral with a delta function. Right? I'm going to tell you very quickly that because this is a product, the value of this funny ratio, when I'm not near my peak, when I'm away from my peak, the values of that function aren't at all important because they're being multiplied by 0. The only place where their values come into play is near k0. So I can simply replace them with their value at k0. So what I want to do then is to take that then as essentially a constant for the purposes of my remaining integral. And then it being constant, I can simply factor it out of the integral. Now the best way to recognize the fact that that's constant and to make that factorization, as we had seen before, is to say, well, I've got a product of the magnitudes becomes the magnitude of the product becomes the product of the magnitudes. And then this term that I have, I can pull it out of my integral because I need to evaluate it near my peak because that is where it becomes relevant. Near k1 equals k0. So what I'm left with then, if you're following the logic, is I just have that factor that has factored out, and the remaining integral is going to give me something very interesting. So I will have this difference, k1 minus k2, over k1 plus k2. That is going to be squared when it comes out. It's modulo squared, but it's a real number, so that will be just squared when it comes out. And of course, we will evaluate it for the momenta of the packet that I'm sending in. But the remaining integral, I hope you recognize, and here I'll square it out as 2 sigma squared on pi. Then it becomes to the 1/2 power times my Gaussian integral. And hopefully you may recognize this. You could work it through as a Gaussian integral, or you simply recognize, well, this was the integral of the weights of the incoming packet, which is being by design as a normalized incoming packet. So this entire expression here evaluates to 1, and I have a very simple answer for my probability of reflection. All it is just the size, right, in front of the reflected piece, but squared because we always get probabilities by squaring things in quantum mechanics. Very good. So that finishes our formal analysis of this problem.